Good afternoon, students. I am Basub sir. Today I am taking a class on moment of inertia. Today I am discussing an important topic. The topic is theorem of perpendicular axis. Very important topic. Okay, the reduction of the theorem is also important. That is, the proof of the theorem is also important. So let us see the theorem first. It states if I axis, that is moment of inertia about x axis, if I axis and I y be the moments of inertia of a plane section about two perpendicular axis meeting at O, the moment of inertia I z, that is moment of inertia about z axis, about the axis z axis, perpendicular to the plane and passing through the intersection of x and y is given by I z equal to I x plus I y. That is, we have to prove that I z equal to I x plus I y. Okay, so the main part of the theorem is if this is the figure. If I x is the moment of inertia about this axis I x, and I y is the moment of inertia about this axis y axis, then the moment of inertia I z, that is it is that moment where the axis z axis is perpendicular to this plane of the figure. It is a two-dimensional figure. The z axis is the perpendicular to the figure where the x and y axis is present. So the IZ axis, that is the moment of inertia about z axis, is will be equal to the moment of inertia of x and moment of inertia about y summation of moment of inertia about x and y axis. You have to prove that. So z axis is the perpendicular to the plane. Okay, and now let one small lamina P is the small lamina, that is a small part of the total area, small lamina, and whose area is dA. The total area of the lamina is A, small a. So the area of the lamina is dA. Okay, now the coordinate of P is x and y, that is along x axis it is x, this is x or this is x, and along y axis this is y or this is y. So coordinate of P is x and y along x and y axis. Now consider a plane OZ. This is OZ plane, that is z is perpendicular to the OX and OY, perpendicular to OX and OY, I previously told. Now let R is the distance from the Z plane, OZ plane to the lamina. R is the distance. Okay, lamina P distance from OZ plane to lamina P. So therefore OP equal to R. Now from the geometry of the figure, as this is 90 degree. So as this y, this x, this is 90 degree. Okay, so from the geometry of the figure, we can say r square equal to x square plus y square. Okay, now we know that moment of inertia about the lamina P about x axis is as I x equal to dA into y square, as moment of inertia equal to area into distance square, and moment of inertia about moment of inertia of the lamina about x axis. The lamina P about x axis will be as the distance from x to P is y, and the area of the P is A. So dA, small area dA. So the moment of inertia will be dA into y square, distance square. So moment of inertia is dA square. Similarly, moment of inertia about y axis will be dA into x square. So, and similarly we can say that moment inertia about z axis of the lamina, it will be as this is here, this r is the distance and area is the dA. So moment of inertia about z axis, that is I z z, will be equal to dA into z square, sorry, g into r square, r is the distance from P to A. Now, as earlier I have proved that r square equal to x square plus y square, so here dA we can write instead of r square equal to x square plus y square. Now equal to, we can say dA equal to x square, sorry, dA equal to dA into x square, so equal to dA into x square plus dA into y square. Now, as earlier I have said that Ix is equal to dA into y square, so and dA into x square to Iy, therefore we can write as Iyy instead of dx square plus instead of ixx. So therefore Izz equal to Iyy plus Ixx. So we have to prove that Izz equal to Ixx plus Iyy. Now it is proved that Izz equal to Iyy by Ixx. So here we can write as r square equal to x square plus y square. Here we may write as may write I equal to area into distances square. So actually therefore Izz equal to Ixx plus Iyy. Iyy, or it may be Iyy plus Ixx, or it may be Ixx plus Iyy. So if you can understand that what is the theorem is, if for a plane area, if if the moment of inertia about two mutual perpendicular axis x and y is given, then any other axis which is the perpendicular to the plane of the first two axes, then the moment of inertia about the third axis will be equal to the moment of inertia of the summation of moment of inertia of the first two axes. So it is very important theorem. It also the formula is very important for any type of problem. Very important for to solve the problem of moment of inertia problem. It is very important. This problem is very important to solve any type of problem in moment of inertia. And also this theorem as well as the theorem is very important, as well as the deduction or the solution or proof of the theorem is very important. To you have to practice this theorem very well, and write down sometimes to in your exercise book to practice well, as you to remember good, and for preparation for the exam. Okay, so this is the theorem of perpendicular axis. In my next class I shall discuss the next very important theorem. The theorem will be as the theorem of parallel axis theorem. It is also very important, and this theorem and the theorem and the proof of this theorem also be very important. Okay, thank you.